Hey there, welcome to our proposal for our research project for our marine engineering. We are mechanical engineers and we have researched and discussed and come up with a proposal for maritime engineering and safety design, incorporating the two. Let's get started with some introductions. I'm Nathaniel Jeter, I'm the team manager. I help direct all the entire project and, of course, all the team members.
I'm Dylan Engel. I'm the team facilitator. I make sure that we get all our work done and it meets the standards it needs to be.
My name is Juan Aguilar. I'm the research facilitator, and all I do is make sure the research that we're doing pertains to our project at hand.
Our proposal is we had a whole bunch of initial proposals we looked at, including ship engines to make sure that they are the most effective as possible. We had ways to combat corrosion and prevent it. We had one that dealt with ocean physics to make sure the waves and the movement of the water and all the storms would not affect whatever machines we put out on the water. And then we also have raisable bridges that we had originally to make sure they are as strong and safe and durable as can possibly be.
Yeah, so the proposal we decided to research was, as previously stated, based on safety in marine engineering environments. We chose to base researching this because uh, the ocean environment is full of factors that increase the risk of harm to operators and mechanical systems in marine environments, and it's not a commonly researched or thought of area. And so, identify the research on safety measures to implement mechanical systems would be very important, especially considering us who will be designing such systems in the future. It encompasses an aspect of mechanical engineering that is not often the first object of consideration, yet is important to the final project.
For our final thesis proposal, there were four aspects of safety and how it is involved with mechanical systems on water. That first aspect is bearings within a ship and how they can become more safer and reliable and lead to more durable systems. Additionally, we considered hydrogen sulfide and how organic matter in maritime environments leads to the production of toxic gas. We also considered biofouling, which contributes to the production of hydrogen sulfide as well as contributing to the failure of systems. And lastly, but importantly, is emergency equipment on a ship and how that can be integrated into ships safely and efficiently.
So safety equipment is one of the big things mechanical engineers have to deal with, especially when it comes to aquatic nature and aquatic buildings and anything on the ocean that they design, because they are so much further away from the normal forms of help, such as the fire department. By state law, most anything in Texas has to have some sort of safety precaution signs as well as equipment to protect them from fire, damage to any sort of vehicle, and bodily harm. And mechanical engineers are recruited to make sure that all the systems are properly in place and that everything is up to date and that all the symbols, as you can see here, are in place. You have to have first aid stations, fire extinguishers, lifeboats are very common, and you also have to have certain radio systems are required for any ship that goes out onto the sea. Now, we on our boat tour saw the Royal Caribbean Cruise Terminal, which has quite a few of these plans themselves. They are made out of flame-resistant materials that get checked every few years just to make sure they're still structurally stable, especially with all the harsh weather that we have down here. They have fire evacuation plans as well as very high-quality fire detectors to prevent and notify any fire departments that need be if there is a fire that breaks out. And they also have clearly marked exits that allow for the easy funneling of people out of the building in case of an emergency. Another place we saw was the Gulf Cooper Dry Dock, Copper Dry Dock. This one was designed by mechanical engineers to help keep to store boats outside of the water, but for the larger boats. Um, and it was designed with these systems in mind to keep it safe. Again, the fire detectors and the different deterrents, since this time you won't be able to get the fire department to them. It was also designed with very strict procedures that are taught by all the different personnel on board and taught to and taught by all the different personnel on board to make sure everybody knows exactly what to do if there was an emergency. It is designed with life rafts that you can see on the side. They're the little orange parts on the side so that in case of high waters, in case of any sort of emergency, they can get out. There are proper protective personnel equipment required, like hard hats and safety glasses, and in most cases, gloves as well, just to avoid any bodily harm. And then there are regular structural integrity checks and maintenance to make sure it stays up to date and stays safe.
Hey there, I'm back. So I'm here to talk about hydrogen sulfide and its dangers on a ship and how that can be identified, where they're sourced, and how they can be prevented. So hydrogen sulfide is a toxic gas produced by bacteria that feed on organic matter in any place that a chemical or organic matter is left to decompose on a ship. So anywhere that this bacteria is and something it can feed upon, the bacteria will release this toxic gas. This gas is often found in places such as ship bilges, the refuse of routine cleanings, and wherever organic materials left to decompose. This gas is dangerous because of the health risks it poses to operators and anybody working on a ship. The higher the concentration, the worse it can affect the person, even to death. So, hydrogen gas it comes from the bacteria as demonstrated by this study. So this study was conducted by the Department of Defense back in 1995, and a research team was given the task of finding where hydrogen sulfide gas was produced, how it was produced, with the idea and intention of being able to mitigate the issue. So as you can see, the first graph shows how the production of the gas without bacteria or the material that it feeds upon. The second one shows only bacteria, and you can see that both of these show very little production of gas. And finally, the third one, when both are present, live bacteria and the material that it feeds upon are both present, the production skyrockets, which can lead to even more fatal possibilities for any operator on a ship. So how can we mitigate this? So we hypothesized, and the study also had its ideas to offer. We posited that the ventilation, properly ventilating enclosed spaces, can prevent the buildup of hydrogen sulfide, in addition to reducing the use of oils and lubricants. Proper cleaning of anything from using the correct detergents and clean cleansers that will not be fed upon and to produce this gas, as well as techniques that prevent excess use of these chemicals, in addition to the proper disposal of anything that's produced from cleaning or just from leaking. All of these to prevent the accumulation and or production of this toxic gas. Now, something else, an additional topic that can contribute to the production of this gas, but is also its own problem on its own, is biofouling. Biofouling is the accumulation of any organic material on a surface, a physical surface on a ship. And so there's two types. Microfouling is a slimy biofilm, and it's a precursor to macrofouling, which is the accumulation of large communities of mobile marine organisms. So both of these on a ship contribute to decreased efficiency, rapid breakdown of systems, so the durability goes down. In addition to being a source for the hydrogen sulfide once this stuff decomposes. So, how to prevent biofouling in design? There are many ways, including one, elevation, which decreases proximity to water. So these pictures are sourced from our boat trip that we took around the Galveston Harbor. And one of the tactics we were able to observe was this oil rig. As you can see, it is elevated above the water, which, among the many reasons it is elevated for that reason, decreases its proximity to the water, which is carrying all these organisms that, will attach themselves and contribute to the accumulation of this biofouling. In addition, skeleton structures, as you can see in the cranes in the second image, minimize niches and hard to reach spots on large structures by minimizing the surface area. In addition, these structures are also painted and treated in a way that will prevent them from accumulating too much biomatter. Second, some more pictures from our trip. Shear surfaces, as you can see in the first photo, allow for easy cleaning. So anything that does accumulate, because something will accumulate, can be easily scraped off or cleaned off. No niches. Finally, metals, plastics, and concrete are materials that are strong and can receive biofouling without being damaged significantly. So this ship that you can see here in the photo has been there for about 100 years, since the 20s, yet it is still in remarkably good condition. Now, it is degraded and dilapidated, but it is still holding itself together, and the parts that were made of concrete, material in question, have not received as significant damage as one would expect over hundreds of years, even with organisms growing on it, as can be observed somewhat in the photo. Now, finally, you can see that all of these photos are sourced from industrial port area, which just goes to show the importance of, as mechanical engineers, the importance of considering these things while we design our systems, because they will be used in frequently frequented, you could say, areas for ships and the shipping industry in general. So it's important for our systems to be able to accommodate ships for many years, as the ones here are doing, and effectively and efficiently without too much decrease from biofouling.
I'm Juan, and I'm here to talk about the literature I researched covering the bearings within a metal ship. In this slide, I'm presenting the scientific evidence that supports my topic, how material selection influences efficiency and environmental impact in ship design. The tables here show a clear comparison between traditional white metal, oil-lubricated bearings, and newer polymer-based bearings. Oil-lubricated systems contribute to over 80 million liters of marine oil pollution every year due to corrosion and leakage. These systems also create higher friction, which causes greater power loss. Meanwhile, the data on polymer bearings, such as PTFE and carbon-reinforced proxy, shows that they perform with significantly lower friction and resist corrosion far better in seawater. When you scale this effect to 3,000 ships over 20 years, you can see that you save over 1.6 million tons of fuel and 160 million liters of oil. This evidence demonstrates that materials used in a ship's mechanical system directly affect both performance and environmental impact. So as you can see here on the left, you have the table that compares white metal, which is traditional, to polymer bearings. You can see how they differ in efficiency and how it will affect the ship, while on the right, you have a table that as revolutions within a ship increased, which is your x-axis. On the y-axis, you have the power loss. So as you can see in the table, the white metal, which in the legend is shown, has the greatest power loss amongst all of the polymer and carbon reinforced proxies used. So this shows that even though something as simple as bearings within a ship, it still has a great impact as to the efficiency of that ship in a marine environment. On the slide, you can see the picture of a Gulf Copper dry dock and the GPS screenshot that accompanies it. A dry dock is a place where marine engineers and technicians see firsthand how ships actually hold up over time. These dry docks expose everything normally hidden under the water where the ship lies. This includes shafts, bearings, seals, and all the mechanical components that we don't normally see. This is where engineers will routinely find corrosion damage and friction to the ship exposed from salt water. This image represents a way to implement the real-world data I showed you in the last slide. The issues we discussed aren't just necessarily numbers in a study, but are things that actually happen to ships. Engineers in dry docks are the ones who have to repair the corroded metal, clean up oil contamination, and replace inefficient parts. This directly reinforces a big part of our thesis that mechanical engineers need to be able to select the materials that best fit for ships in the marine environment. Polymer-based bearings and seawater lubrication systems are something that do just that. Scientific evidence from the literature and the real-world perspective that I'm showing you here shows why material selection is critical to creating more efficient and longer-lasting, responsible ships.
So thank you for watching. This has been our presentation on our proposal for extended research on these various aspects on how safety measures can be implemented into mechanical engineering designs in the form of additional safety measures, um, as well as preventing the formation of hydrogen sulfide and biofouling, as well as using better bearings in our designs. So thank you for watching, and I hope this has been enjoyable to see. Have a good day.